With the green light on, it should be on.
Hello. Hello. Just testing. Is it okay like this? Okay. Sorry, I was waving to John in the back. But I can also wave to you. Hi. Sorry. Okay. Sure, whenever you're ready. You're the boss.
Good afternoon, everyone. So we're happy to start another lecture series. Alejandra Castro from the University of Cambridge is joining us. We're happy to have her here. She's going to be talking to you about topics in AdS CFT. Alejandra.
Thank you. Thank you very much. And yeah, you can still hear me. This is okay, volume-wise? Okay, good. Thank you for the invitation. It's a great honor to be here and tell you a little bit about AdS CFT. But before we begin, I'm basically in a room full of strangers, roughly speaking. I barely know you. And so to get to know you, a little bit of a poll. So how many of you would consider that in some definition that we can specify as we go along, work on AdS CFT? Raise your hands. Okay. Okay? Good? Okay. Just to have an idea, I know there's a mixed batch of people, and it's not a good assumption to assume that nowadays everyone in FTH does AdS CFT, but it can be. Now, out of those that self-identify as AdS CFT, it's fine. Like, okay. Okay. How many of you would consider put yourself? You can only pick one. Don't raise your hands twice. So this is a binary choice. How many of you would say you're on the CFT side of things? Okay. And how many of you would say that you're on the AdS side of things? Okay, very good. Okay, so I think from that point of view, one thing that I assume, and I think it's okay, but if it's not okay, please let me know, and also based on the previous lectures, is that this is topics on AdS CFT, not introduction to AdS CFT. So I'm roughly assuming, so this is my fault, I'm roughly assuming that even if you don't work on AdS CFT, you kind of know what's going on. Is that a good assumption? I think from the raising of hands. Otherwise, let me know, and I'll try to fix it somehow. But I also know that you already had lectures on AdS CFT in the previous week, and those were also not introductions to AdS CFT. So I think it was. Only that. Okay, but well, in any case, I do think that these, even if you don't know anything about AdS CFT or you don't feel comfortable with it, I think the way that I'm going to be talking about it will be hopefully in a way that if you know about general relativity, kind of understand what the word AdS is, it will be okay. And then the other assumption, which I think it's a stronger assumption because you had many lectures on this, is that you'll have some understanding of conformal field theories, And so I saw that also in the lectures, so I think that will be okay. But in any case, these are lectures, this is informal, so please, if something is not clear, I'm making too many assumptions about what you already know, just ask me, okay? This is what we're here for, so that you can interrupt me. And yeah. But in any case, so let's specify, this can be like, this is the worst title for a lecture. It basically means nothing. It's like, what is this lady going to be talking about? Who knows? Nobody knows. Oh, okay. So maybe based on my previous work, this is a lecture on AdS3, CFT2. Okay, so that's what we're going to be talking about. And basically, in the context of the school and what we're going to do is basically what I want to illustrate by talking about AdS3 CFT2 is basically the power of symmetries in holography. Okay, because this is a school about symmetries. And so we had to pick an instance of AdS CFT where symmetries are just like in your face and they're all everywhere. Now, in general, AdS CFT as a subject is a subject that in many ways is controlled by symmetries. Because as you guys already know, conformal symmetries are a special class of QFTs for which many quantities are fixed by conformal invariance. And then in the context of AdS CFT, just in general, the fact that conformal field theories are so powerful as field theories, they basically dictate rules just based on symmetry arguments about how you should define observables in gravity. This is one of the amazing things about AdS CFT. It basically gives you a way, it dictates rules to define observables in quantum gravity. Okay? And this is clearly my interest, why I'm fascinated about AdS CFT. I think it's a wonderful subject. I feel like you should never apologize for working on AdS CFT. Never do this. Never start a talk by saying, oh, I'm doing AdS CFT, but we live in flat space. No. Okay. It's like, I hate when people say that. Sorry, I'm being recorded. But in any case, this is a very powerful thing. In AdS CFT, symmetries are very, very insightful in general. In any number of dimensions, they're quite insightful. So they're giving us an organizational principle about how we deal with the correspondence. Now, in the special case of AdS3 CFT2, something even more wonderful happens. So if I do a plot of an understanding of AdS gravity based on the number of dimensions, so we start in 2, 3, 4, 5, whatever, up there, and then you plot it against how much symmetries affect the correspondence. Roughly speaking, you get, it looks something like this. Like there's a really big spike in AdS3. So symmetries are extremely, extremely powerful. And then in AdS2, they're also quite powerful, but there's a bit more challenges there. So in AdS2, you use a lot of symmetries, and then it kind of goes down as you go higher in dimensions. Okay, they're useful. They're always useful, but they kind of go down. Now, ironically, sorry, if I do a different plot, again of AdS, and then if you ask me, okay, given that we have so much symmetries, how much do we know about the dual CFT? This plot is kind of reversed in a sense. It's kind of embarrassing. So again, here I'll put 2, 3, 4, 5. And as you go up, of course, we know a lot of things about CFT2s, but in some sense, even AdS2 is in a better shape. And then it really goes down in terms of knowledge, and then it goes up. I think the peak is in AdS5, and then maybe it goes down again a bit. I don't know. Just something like that. What's that? Yeah, it's even negative. I feel like I'm very frustrated. Yeah, it's like it goes all the way down. And so I hope one of the lessons of these lectures, I hope if I get there, is to understand how we can cure this, okay? Because basically, in this area of AdS3 CFT2, we have a luxury of tons of symmetries, but at the same time, we have a crisis, okay? It's just too good to be true. And my lectures basically are going to illustrate this. It's going to illustrate the crisis of symmetries when we have too many of them, and then it kind of makes it difficult and sometimes to quantify dynamical aspects of the correspondence and aspects of the correspondence that involve strong coupling in particular. And so, so basically the goal here, before I give you a precise outline, because I'm pretty sure I'm not going to follow my outline, is to basically have a control and in some sense overrule the symmetries, okay? So perhaps in the other lectures that you listen to and the rest of the aspects of symmetries that you've been studying is basically highlighting to you how that's so powerful, how you can learn so much. This is also going to happen here, but at the same time, we'll have to like chill a little bit and be like, okay, this is getting ahead of ourselves, and and we actually will see that it gives us quite a bit of headaches. But in any case, so in this context, the goal, I will have 3 goals in mind. So I will basically try to present to you various results of AdS3 CFT2 that are controlled by symmetry. And as we do that, basically what I want to highlight as we present these results and we analyze them is to understand how it challenges the correspondence. And basically, what I want to keep in mind for you is to introduce the concept of what does it mean for a CFT to be holographic. Okay, so what is basically the fundamental mechanism behind AdS CFT? And in that context, how the CFT can tell us, basically, I want to use the CFT as a definition of an EFT of gravity, okay? So in this context of AdS CFT, basically, so sorry, I'm repeating myself, but what I want to have an idea is that if I see the CFT as the definition of what quantum gravity in AdS is, what does it tell me about what are possible low energy descriptions of AdS, okay? Does anything go or not? And this is part of what we're going to discover. Okay, what does it mean to have a theory of quantum gravity with a UV completion, with a theory that is unitary in these realms? And then the third goal, hopefully, that I'll get to it, is basically a way how to implement and solve these obstacles. Okay, so we'll find some obstacles and we'll try to get rid of them as much as we can. I start with the wrong positions of blackboards, but okay, that's fine. So from that point of view, the outline, roughly, I know I have 4 lectures, but I'm pretty sure I'm not going to be able, I will overestimate how much I can cover. So basically, I decided to divide this into 3 parts. Maybe there might be a 4th if I'm fast enough. But roughly speaking, what will happen for today is that today we're going to just study AdS3 gravity. Okay? So today there's going to be basically no conformal field theory. So I know probably some of you already know quite a lot about AdS3 gravity. Do you? Raise of hands. There should be at least 2 hands raised. Come on. Okay. Okay, no, but that's great. So then we'll talk about AdS3 gravity. and so that everybody is on the same footing of like what are these properties, why the symmetries are so powerful. And then we will explore the gravitational like smells in the CFT. And then as we try to implement these things, I'll show you basically how a corner of conformal field theories, which go under the name of symmetric product orbifolds, can be a good way how to overcome some of these challenges, okay? And test the lore behind AdS CFT as a playground. So basically, during this lecture, here we will be very hopeful. It will be very fun and exciting, and you guys will be like, oh, wow, that's great. AdS3 is great. Here we will get to a moment of crisis and panic, roughly. I'll show you why. And then maybe here we can find perhaps a cure. Not a full one, but in any case, that's what's going to happen to you. Now, I should say from the get-go, this is one corner of AdS3 CFT2. This is not everything that happens in AdS3 CFT2. There's tons of things going on. And so please ask me questions. I'll try to highlight other aspects of research and developments that are happening in AdS3 gravity that are quite exciting. But I do have limited time, so I can't cover everything. And I made a choice of covering roughly these topics. But there's also 2 years ago, there were also lectures on TASI on AdS3 CFT2. They have a bit of overlap with this, but then they also discuss other corners of it. So if you're very excited and motivated, you can watch the videos of Alex Maloney from 2 years ago on the subject as well. Okay, so are we ready? It's always tough to do it after lunchtime. Then it's like we're all kind of like, the food, the buffet, so many options. Ice cream. I didn't even have ice cream, but okay, we're ready, right? Yes. Okay. Great. Okay. So now I'll do this in the right direction. So we'll start down. Okay. I think. Oh no. Did I want it to? Doesn't matter. Okay. Whatever. Okay. So let's start talking about. Let's go through part 1. Basically, the power of symmetries in AdS3. Okay, so what do I want to say about AdS3? So many things. Okay, so the first thing, when you start describing a theory, well, at least a gravitational theory, from the low energy point of view, I want to start talking about an action principle. Okay, so when I tell you that I'm going to be studying gravity in 3 dimensions, in general, I have in mind that I'll have a metric and some matter, some fields phi that I'm describing here, and this action, starting from a low energy point of view, I will split it into 2 parts. So basically, I will always have in mind that there's a part of the low energy action, which is the Einstein-Hilbert action. And there's a part that basically couples matter fields. So here phi describes a collection of them, not necessarily one, not necessarily a scalar, but there's basically matter fields coupled to gravity. Okay? But what we're going to do for the rest of we'll come back to this matter part of AdS3. We're not going to forget about it, but I first want to focus on this Einstein-Hilbert part. Okay, so let's write down what that action is. So just to set up the notation, and if someone wants to, in their free time, because I'm sure you're full of energy and good spirits to do some computations, right? Right, yeah. Yes, I can feel the enthusiasm in the room. If you wanted to check my conventions and tell me, Alejandra, that minus sign, that's wrong. Here's the Einstein-Hilbert action with a negative cosmological constant. minus 1 over L squared. Okay? Okay, so the equations of motions also of this theory. Which imply that the Ricci scalar is 6 times lambda and R mu nu. Okay, very good. So first quick test. What is something special about writing down gravity in 3 dimensions? Does anyone know anything? Minus the 3 persons that raised their hand. Sorry. There's no graviton. Is that what you guys were? Why? Why? Sorry, the question was, sorry, part of the answer was, yeah, so there was a statement of like, there's no gravitons, and then there was a statement about being topological, and I'm asking why.
Because the Riemann tensor is fixed by the Ricci.
Why?
Because if you count the number of independent components, it's like 6 for both of them.
Very good, very good. So the answer to the question is basically the Weil tensor in 6 dimensions identically vanishes as an identity, which is also the same answer that I got, is that if you count the number of independent components of the Riemann tensor, it's equal to, of the Ricci tensor, well, if the Riemann tensor is the same as the Ricci tensor, it's the same as the metric. So the claim, or well, a fact, it's not a claim, it's a fact, the truth of life is that the Weil tensor in 3 dimensions vanishes identically. This has nothing to do with equations of motions or any theory that you have. You open Carroll is one of the problems in the chapter of curvature, okay? And I even given us an exam when I taught GR, and the students hated me. But it's, it's an identity you can basically just show by counting that the Weil tensor vanishes in 3 dimensions, just in this exact identity. And so then that tells you, as I was told, that the Riemann tensor basically is fixed by the, the bracket on the wrong position. It's basically fixed by the Ricci scalar and the Ricci tensor in this way. Okay? So this is always true, just as a matter of life in 3D. Now, if we now say, in addition, that we're satisfying the Einstein's equations, so now if we, in addition to this, now we plus impose the equations of motions, we can find that the Riemann tensor has a very simple expression it's basically this, okay? So any solution to the Einstein's equations will have a Riemann tensor that is of this form, okay? And this is the expression that basically tells you you don't have any local degrees of freedom, okay? Why is that? So this Riemann tensor, have you ever recognized a Riemann tensor that looks of this form? It's also in Carroll, chapter 4, 3. Yeah, this is the Riemann tensor for a maximally symmetric space, which basically tells you that any solutions to the equations of motions is locally related to AdS3. Okay. And so therefore, the statement is It's a topological theory. Okay. Oh, and I should say, sorry, we're looking this pure AdS3 gravity. So basically, in the absence of matter, it's a topological theory. Done. There's nothing. There's no gravity. Thank you. Now we can all go home. It's a very short lecture. This is power symmetry. Okay, just a few things to say here, just to note. As probably is clear from the expressions, this is, of course, not special to AdS. This is, of course, also true if you have zero cosmological constant or if you have a positive cosmological constant. There's no local degrees of freedom. And the second important remark is that this fact perhaps was the inspiration back in the 80s to connect the Einstein-Hilbert action to Chern-Simons theory, which, as maybe many of you know, is another topological theory in 2+1 dimensions. I am not going to talk about this, sadly. I love this subject. I love how gravity is related to Chern-Simons theory. I have spent way too much time thinking about this. It's a great subject, but it will not be the subject of these lectures. So if you're interested in knowing more about the relationship between gravity and Chern-Simons theory, I'll be happy to talk to it. But that's all I'm going to say for the lectures. Okay? So there's these two aspects. Now, what do we do now? So we have a topological theory. What is a theory made of? What can we ask? There's no gravitons, and everything looks, based on this statement, everything looks locally like AdS3. So I was suggested that we can just go home. It's option 1. Maybe that would be fun. So exactly. So I was suggested. Sorry, the question was like, maybe you can sum over topologies. And that's actually a great point. So and it's part of a lot of what's going to happen today. So the fact that a theory is topological, I hope that nowadays doesn't imply that it's boring or it doesn't have any contact. It means that your degrees of freedoms are just organized in a different way. And so from that point of view, this is where symmetries become very powerful. It basically tells me that if I want to characterize the classical and even at some level the quantum phase space, I can do it. And there will be basically everything that I will do. Basically, I will have tons of control. I can basically what I'll do. This lecture will just be trying to illustrate to you what is this phase space, and it will be divided though into 2 categories. So there will be a perturbative part of this phase space, and this is what goes under the name of boundary gravitons. And then there will be a non-perturbative part of the phase space. Which basically here, there's many things that can happen here, but for the purpose of these lectures, what I want you to think of is in terms of black holes. Okay? And this is where the topologies are going to come in this non-perturbative part. Okay? And so then, given these facts, then the challenges as I try to characterize the phase space, and well, it's a challenge of gravity in any number of dimensions, since I know that everything is going to look locally like AdS3, what we will have to do is basically, so the challenge here is to differentiate between solutions. I.e., how to define observables. Okay? This is why perhaps AdS3 gravity has some advantages over these 2 other cases. So in these 2 other cases, It's not that you can't do anything, but in the case of AdS3, I can tell you a very nice story about then how do we distinguish between different solutions, different manifolds that you might have, given the fact that everything looks locally like AdS3. So I was already suggested you should look at topology, but basically the question is, should I look at other aspects of it or not? Okay? And so as we do that, this means that, first of all, there will be two, basically, what we're going to do, is that we're going to basically acknowledge that everything is connected by a diffeomorphism, but we basically want to make a distinction that there will be every solution that we'll care about will be characterized by being a large diffeomorphism. And in this context, what we're going to learn is that there's two types of large diffeomorphisms. There's ones that act non-trivially on the boundary of AdS. And this gives rise to the notion of asymptotic symmetry groups, which I know Andrea taught you all about it in flat space last week. But it also shows up in AdS, and in AdS3, it's quite important. So there's a notion of asymptotic symmetry group. And then there's the notion of basically, for what I'm going to do today, of diffeomorphisms that are not connected to the identity, which basically change the topology. So those are also called a large diffeomorphism. So there's a little bit of abuse of language in the field. When someone tells you you have you're in the presence of a large diffeomorphism, and you're not quite sure what they mean, they might mean one of these two things. Okay? There's an overlap in this definition, as we will see, but this is basically large diffeomorphisms as jargon is used in these two contexts, either diffeomorphisms that act non-trivially at the boundary, or actually diffeomorphisms that change the properties of the space-time. Okay? Very good. Great. So, because black holes are fun, we're going to start here. So what I'm going to do first is tell you about these non-perturbative solutions. And because all of you are expert in asymptotic symmetry groups, then I'll touch upon very quickly on these because, yeah, right? Right, okay, yeah. Okay. So let's start talking about these non-perturbative solutions. And just to check how quickly I'm talking, because you guys should ask more questions. Yeah, you definitely should ask more questions. Otherwise, I'm going to assume that all of this is really a piece of cake and like I'm just cruising through. Probably it is. No? Okay, then ask questions. Okay, question there in the back.
What does large mean here?
Those two things. So sorry, the question was, no, but I'm not joking. So that's what I meant by these 2 points here, to define what large means. So large can either mean that the diffeomorphism will act non-trivially in the boundary, which it will be very manifest when I talk about these perturbative parts, or it can mean that basically like a quotient of the space. So it's changing some property of the manifold, and so it changes the topology. So it can mean either of those 2 things. And we will see that those type of diffeomorphisms have an impact on the observables. So we'll see what are those observables and how they change it, and then you can say, these 2 solutions are different because when I act with this large diffeomorphism, it changes some conserved quantity that you have or some action that you have. Yeah. Okay. Yes? Maybe. We'll see. This is part, like, I think, so Witten back in the, oh, sorry. Sorry. So the question was, given that the theory is topological, should I expect a TQFT at the boundary? Was that? after quantization, after quantization. This is an excellent question. The answer is that we still don't know yet. So back in the 80s, when Witten wrote this paper connecting it to Chern-Simons theory, there was an expectation that maybe that was going to be the answer. Because we know Chern-Simons theory, in a sense, when you put it on a manifold with a boundary, is the first example of holography. It's not gravitational holography, so it's not like fancy and stuff, maybe. But it's a holographic correspondence, okay? So you have a theory in the bulk, this Chern-Simons theory, and then the interesting degrees of freedom live at the boundary, and these like boundary degrees of freedom. You have either a WCW theory living at the boundary and things like that. So it's an example of holography, just so you know. And so back in the, usually it's done with compact gauge groups, and then the rules are much more clear. But in this case, the rules are less clear because we're dealing in gravity. So as I'll tell you in a moment, the gauge group is non-compact. And so then the rules are a little bit more iffy about what does it mean to quantize this theory. And so, but back in the 80s, when Witten made the connection with Chern-Simons theory, the title of his paper was like, 3D gravity is exactly solvable theory. He did not solve it, but there was always the expectation of like, oh, we should be able to like solve it, and we should be able, maybe this is the right answer. And I hope that by the second or third lecture, you will be like, ouch, these things are not working out. So far, we have not been able to make that connection. And I'll show you why. Because, and this is also why gravity is related to Chern-Simons theory, but it's not actually quite Chern-Simons theory. So I don't have evidence for that claim. I only have obstructions for you. But if someone can overcome those obstructions and see, oh, what are the rules to quantize it such that that's true, that will be great. But so far, yeah, we're not there yet. Sorry. Yes, you first, and then the guy in the back. Sorry, I don't know your names yet, so just pointing to. Right now, we're only going, for today, I'm only going to look at classical solutions, but we will quantize them. So, because I will have the capacity of quantizing them. But we will first construct the classical phase space. So we'll basically look until we're bored. We're going to look at the solutions of the metrics here. And then we'll say, and then I will tell you something about the quantum theory.
You mean it's on the boundary
Oh, those are on-shell. They're going to be diffeomorphisms, yes. Sorry, I was being asked about if we're going to do both classical and quantum aspects of the phase space. And they're in the back.
So why do we call it the second class of diffeomorphisms?
So I was sorry. No, it's yeah. So this is where I put my physics hat, and I take off my math hat. Although I am nowadays in a math department, but I'm a physicist.
Don't forget your fruit.
So the question was, thank you. The question was, why are you calling class number 2 a diffeomorphism? I will write for you a diffeomorphism. It's just that it's not defined everywhere. It has a point where it becomes singular. But there is a transformation that implements this quotient, at least for the simple examples that I'll do. And there has to be a diffeomorphism in some sense, at least patch by patch, because everything that solves the equations of motions looks this way. So it means that at least in some local chart, you'll be able to write a diffeomorphism. Yeah, there will be local diffeomorphisms. No, that's if you can write like one, then there's no difference, right? You didn't do anything. If the diffeomorphism is everywhere defined, then exactly. So that's also why I stress here that everything looks locally AdS3. So when I write the diffeomorphisms that relate the solutions to make manifest that every solution at the end of the day has this form, they're just local diffeomorphisms. So just to illustrate that there's a patch of the geometry by which you can see the relationship and why it's always connected to global AdS3. Any other questions?
You can classify this solution space with its
Okay, I'm being asked if I'm going to classify it. So on the cylinder, I'm not going to consider every single possible topology. So that will take me yeah, we'll be here for quite a while. And if yeah, so I'll look at the simplest ones, because I should have said maybe here when yeah, sorry, I forgot to write down that here in the outline. When we will get to this point, it's basically what we'll be looking at are basically partition functions of the CFT, so the torus partition function. And so then I only need to classify, I only need to discuss the phase space that is relevant for the torus. Yeah. There's, of course, more things that you can do, and that will make you even more confused and upset if you continue studying AdS3 gravity. But the torus is enough to get you already in crisis mode. OK, very good. So the first solution that we'll look at, just to set the stage and the conventions, let's write down, sorry, and was there any other question? No? No? OK, good. Let's do global AdS3. So in Lorentzian signature, what we call global AdS3 is this line element where phi is identified by 2 pi, and time here runs from -infinity to +infinity. OK? Some ways to write this solution, I think it will be convenient. So to also write it in this form. Come up in further lectures where I'll raise the Blackboard in a moment. So OK, so that's global AdS3. And the way that you should visualize it is basically as a cylinder. OK, so time goes up, angle, radius. Okay, global AdS3. Now, in Poincare coordinates, we will write down AdS3 like this. And the reason, there's a sense in which, yeah, I'm writing this characterization because then it will make very clear the group theoretical aspects of what's going on for those of you that are more inclined in this way. And in this parametrization, you can write, yeah, you can make, well, in any parametrization, you can make explicit that this is a group manifold. But basically here, this matrix G is this, which is an element of SL2C. And of course, it has as an element of SL2C, it has determinant equal to 1. OK, very good. So yeah, so those are two characterizations of AdS. And to be clear, the coset here is, so if you view this as a coset, it's not quite SL2C, it's SL2C mod SU2, because there's an ambiguity in the definition of this G. So basically, G, you can always decompose it as H times H dagger. And there's basically an SU2 matrix by which you can redefine H that creates this ambiguity. OK, so that's global AdS3. And written also in Poincare coordinates. And that's all you need to know. OK. Now, the BTZ black hole. So I'll just write it for face value. OK, I'll write down the metric for you, and then we'll discuss what it means and what it means in connection to these statements that we made down here. So second solution, this non-perturbative context, the BTZ black hole. Okay. Should be mentioned, the solution, although it's very beloved in the context of AdS3 CFT2, it was discovered basically before the conception of AdS CFT. And then people ignored it, and many people didn't believe that it was a black hole because of those statements there. And they're like, what is that? Nobody cares. And then AdS CFT came to life, and the world exploded with the wonders of the BTZ black hole. So here it goes. Let's write down the BTZ black hole. There's going to be a lot of line elements. Okay, so in this line element here, I'm abusing notation because I don't want to have 3,000 definitions of R and T and phi, but I hope from the context it will be clear when I'm referring to BTZ and global AdS. But basically, sorry, this is also squared. The lapse function of this metric is given by this, and we'll also write it in this way. I'll define all these symbols for you in a second. And the shift function over R squared. Okay? So that's the metric of the BTZ, where these R plus and R minus are basically the outer and inner horizon. M and J, without any justification, this will be part of what we will be doing. M and J, for now, we'll call them mass and angular momentum, but you should all be very skeptical about, she has not defined mass and angular momentum. So for now, they're just little numbers, okay, constants.
In the definition of N5, one of the R is the R minus.
Sorry, yes, the second one. Yeah. And yeah, so they're just basically two ways how to write things, and let me just relate them. So 8GM they're defined like this. Okay, they're related in that way. Okay, so this you can check. So we can do various things, but there's many things that you can check here. And so, for instance, one thing that you can check, if any of you are fond of Mathematica, check that it satisfies the equations of motion. Okay, we're not going to, of course, we're not going to do it. But this solution basically satisfies the Einstein's equations for arbitrary R plus and R minus, meaning that it complies with everything that I said here on this board. Okay, so it's a solution. Therefore, it should be locally AdS3. Okay? So now let's digest a bit more what this means. So what are some of the properties of the BTZ black hole? Okay, so the first property, maybe the simplest one to say first, we'll use it in a moment, is that basically it has two killing vectors. Which are
partial t, partial.
Okay, thank you. Just to see if you're still awake and with me, or if you're thinking about when is your flight, is it time to get my boarding pass, when am I leaving here? No, okay. Second property is that if you look at this metric, you can get global AdS3 by setting j equal to 0 and m equal to -1 over hg. Okay? So you put those values in there, and you'll get the metric that I wrote down on the other corner. Okay? So in this language, global AdS3 looks like something that has negative mass. Okay. Now, the third property is that if you take r to infinity in this line element, the space is what we will call asymptotically AdS3. So the extra a there means asymptotically, meaning that far away it looks like this, which basically resembles the metric of AdS in point-correct coordinates. Yes?
What will I get if I set j equal to 0, m equal to 0? I thought that's a no.
Poincaré, or what you will call, sorry, I should say, because I'm identifying the angle, is what people call the massless BTZ black hole. But in Poincaré coordinates, the coordinates there that I call set and set bar are not identified. So you also, if you uncompactify the angle, so here phi is periodic, then you will get Poincaré. But otherwise, if you just set m and j equal to 0, it will look like Poincaré, but with an identification. So people call that, technically speaking, it is the massless BTZ black hole. Okay, then, yeah, I told you this solves equations of motions. Okay, so maybe I should just write it. So just so it's recorded. And then property number 5. So when the mass is basically bigger than the angular momentum, these two roots are real. And also I should say I call them R plus and R minus, so I always have like a hierarchy between them. So R plus is bigger than R minus, and they're also going to be positive, I should say, in this regime, okay? And if Lm is equal to the absolute value of j, we call this then extremal solution, which has R plus equal to R minus. Okay? Then, in a sense, I'm also throwing you a fast ball because I'm not really defining carefully nor constructing for you the Penrose diagram, but I think that will be a little bit too long and tedious. So the reasons, one of the basic reasons that I'm calling this a horizon, and in particular the outer horizon, which is denoted by H plus, it's because there is a killing vector, zeta, that is a linear combination of the two killing vectors that I have here, dt and d phi, where for a suitable choice of this omega, which is the angular velocity, which in this context it will be r minus divided by r plus times L, you will have the fantastic property that the zeta is always positive for r bigger than r plus, and zeta is equal to 0 and r equal to r plus. Okay, so this is the killing vector that generates the outer horizon. Okay, so by part of the definition of a horizon is that you have a killing vector that becomes null at some point in the geometry. And then you also have to show that it's global and blah, 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 but okay, I'm not going to do that. You can also show, for instance, that you have that at the horizon, you have a surface gravity. So this is also at r equal to r plus, and then this kappa plus is given by this quantity. Okay, lots of definitions. So now, what else? Last property? No, not last. Oof, so many properties. Next property. Okay, now we have a horizon, and then as an anxious person, the next thing that you do, even before I defined mass and angular momentum, let's do thermodynamics. Because it's so suggestive. So which number am I at? 6, 7. So you can define basically a temperature, which is this kappa plus divided by 2 pi. We already defined, you also will have this omega h, which is r minus divided by r plus times L. You can define the area of the horizon divided by 1 over 4g Newton. Which will give you over 2g. And something that you can check very quickly is that this is going to solve, it's going to satisfy a first law. Okay, because we're terribly anxious when it comes to black holes, and this is always fun to do. Okay, so that's another thing that you can check. Okay, now the next property, so we're getting closer to our statement that this theory is topological and everything is a large diffeo, although I haven't been highlighting it yet. Yes?
Are r plus and r minus always independent of phi? In this case?
Of phi, phi is the angle.
Yeah.
So yes, they're constants. Yeah, sorry, yeah, so and the same as m and j. So this is a static, stationary, so it's a little bit implied here. This is a stationary solution, meaning that nothing depends on time or phi explicitly. So yeah, so r plus and r minus are constants. Yeah, they define the position of the inner and the outer horizon. Okay, so where was I? Good. So then property number 8. Let's take this to Euclidean signature. And when we go to Euclidean signature, so basically we're going to take time to I times t Euclidean. So if I'm very lazy, then it just means that I put a plus there and I write down, maybe, yeah, let's be lazy. Okay. I don't want to write down the metric again, as you guys can note. It takes me a while, so let's not write it. So Euclidean BTC. That, okay. You put an I there, and okay, that's the Euclidean BTC. So okay, that's the metric, easy. Now, when you go to Euclidean signature, then you do have to be careful about properties of the geometry, because now you have a point of the geometry where you have to impose a regularity condition in this Euclidean space. So basically, in Euclidean signature, you get what people usually call the cigar geometry. So if I draw how the black hole should look like, so here I'm having a drawing where this is the radial coordinate, and this direction here will be the Euclidean time. If you inspect what happens to the geometry when you are at r equal to r plus, this will be infinity. You have to impose, the reason why I'm drawing time as a circle here is because when you reach the point of r equal to r plus, you have to impose a periodicity condition on Euclidean time. Otherwise, I would have drawn something that looked like a cone. Okay, and so the regularity condition is basically that you grab your Euclidean time and your angle. And okay, there's an obvious periodicity, which we already stated, which is phi going to 2 pi. Okay, so we know that that's still there. I haven't changed that when I go to Euclidean signature. But then this regularity condition tells me, let me divide this by L so that then my conventions are somewhat sane. Otherwise, I will put L equal to 1 at some point. So the regularity condition here is basically the fact that now I have to identify time and the angle by that amount. And those amounts there are naturally related to these thermodynamic variables that we were talking about.
Just to let you know, we've got about 15 minutes.
You're killing me. Okay. He was telling me that there was 15 minutes left. That's why I said that. Okay, so I guess we'll have to do perturbative states tomorrow. So then I was realistic that I would run out of time. Very.
Too many questions.
It's fine. It's fine. It's okay. It's okay. Ask questions. Ask questions. This is great. This is great. Who cares about symmetric product orbitals? Besides me and Susana, that's the only two people that care. No, I hope many of you care about symmetric product orbitals. Okay, so this beta and theta here are basically related to the th and omega h that I defined there before. But then you can see that this is also very suggestive that if I now define a coordinate set like this, what I'm basically telling you is that there's two identifications where tau is that. So if I had to draw now Euclidean BTZ black holes, what do you think that I should draw based on this? I heard something. I heard a whisper. Solid torus. Very good. So the geometry of Euclidean AdS is that of a solid torus with complex structure tau, given by that quantity here. And the two cycles that I have in play are basically, so this solid torus has two cycles. And so there's basically a non-contractible cycle, the blue one, And because it's a solid torus, so the radial coordinate is going up, this is a contractible cycle. And basically, so let me call this one B and this one A. This guy over here is a contractible cycle when you go around 2 pi and the angle. And this regularity condition, which is also reflected, basically I was drawing the torus in a different cross-section up there. B basically is the thermal cycle, which is the contractible one in this case. Okay? So this one tells me about the size of the horizon. The blue one tells me how big the horizon is in some way, if you think of it in terms of holonomies. And then this one is telling me that as I contract, I don't pinch, the geometry is completely regular. Okay? Good. So the BTZ black hole is a donut, but John doesn't like donuts. You didn't get it. Okay, John got it. Okay. Good. Very good. So that's the Euclidean black hole. Now let's get to this part here. So where's my large diffeomorphism? So we'll write down 2 large diffeomorphisms. And we'll keep the statement that AdS3 is topological. So the last comment about BTZ, and I think I do have the time to say my last comment on BTZ. Yes, 10 minutes. So I was at number 8, number 9. The large diffeos, because at the end of the day, everything related by a diffeomorphism in some way. So let me just write it down for you. So yeah. So because I use set twice, let me call this one, I'll be annoying. And I'll call this one W. So here's a diffeomorphism that relates AdS3 to Poincaré. There you go. Implement, if you want, the way that I wrote it is that implement this coordinate transformation on that line element there. You'll get the star metric that I wrote down. It's all a diffeomorphism. So this takes the metric of Poincaré to the metric of BTZ. But of course, I'm doing something to Poincaré when I do this, right? So we can see it basically. So the defining property of my Euclidean BTZ was that I was doing these identifications, right? And so I'm not giving up on these identifications. They're a defining property of the geometry. And you can see that that identification basically tampers with the periodicity conditions of omega. So that's why it's going to be a quotient. Okay, so when I wrote down those coordinates there, I should have said it. The range of W and W bar, where plus and minus infinity is just a plane. So if you're not familiar, so if I would have drawn Poincaré AdS in the same way that I draw the cylinder there, usually the picture is something like this, the typical picture of AdS CFT, where this is the W plane, and then this is the Y coordinate going into the interior. But now, as I write down this diffeomorphism, you can see that the W now is going to get identified because of the identifications of the torus. And so from the point of view of this matrix G, or in particular the H, so what do I want to write? So basically, the identifications of the BTC torus basically tell me, sorry, I need to move this guy a little bit further up, because I think I wrote it down there, that H there, implement on AdS3 and point correct coordinates, basically the identification gamma times H again, where gamma is this identification, okay? So what am I doing? What is that diffeomorphism doing? It's basically telling me that I'm relating two geometries that are a solid torus. But now what I did, I have a solid torus now with an identification that is -1 over tau. So schematically speaking, what I have done is exchange the contractible and non-contractible cycle. So this is BTZ. This is AdS3. Here I have like what we call, I should say, thermal AdS3, because I'm doing now identification on AdS3. So this guy has complex structure tau. And this one has complex structure -1 over tau. Yes? That this is not a diffeomorphism that is defined everywhere. So for instance, just naively, you can see that it becomes singular when R is equal to R plus or R is equal to R minus. Just as a, like, yeah. So in the context of the question that I was asked before, like this is not a diffeomorphism defined everywhere. In the manifold, it's defined in just in some regions. Yeah. So in that sense, it's large. It's also large, if you want, from this point of view. So I'm enforcing now on that geometry, on point correct, this quotient. I'm making this identification. I'm identifying points that satisfy this condition. The geometry up there did not have any identifications in it. So by relating it to BTZ, I need to have this identification. So that's where you can see, you're changing the topology of the space when you're insisting that these two solutions are related. And that's what I'm illustrating also here. So they're related, and they're related by something that takes this parameter tau to -1 over tau. And this smells like something that you saw the first week. So cute. Gravity is so cute. Full of surprises. Never thought that you would see this. Okay? So in the next 3 minutes, what am I going to say? Not much more, I think, because this is a good ending point. So what I want you to learn from here, basically, so this is an illustration of these non-perturbative solutions. So basically what I showed to you is different classes of solutions. Sorry, I should write down, sorry, that's the thing, because I still have a few minutes. Sorry, so this is how it's related to Poincaré. You might be also interested in how it's related to the global AdS3. Right, yes, you're super interested in how it's related to the, okay. And so if we just do it to global AdS3, instead of going through this funny Poincaré thing, or I should say the thermal global AdS3, and then the angle of AdS, just to be clear, it's I over L. And the time that I wrote there, and so from that perspective, you can also notice, so these things over here are also implementing periodicities on the geometry. So the set is still identified, and this is going to force these angles here to have identifications. And here you can see also the cinch is the thing that becomes 0 when rho is equal to 0. So that's the contractible cycle. And then the thermal cycle is the big one. So F1 is the one that it multiplies the cosh. Okay? So you can see from there, from here it's very clear that phi is this blue one, because you're going close to r equal to 0. Sorry, to rho equal to 0. Okay? So this is how you relate BTZ. You do this coordinate transformation in global AdS3, and you'll also get that space time. It makes it a little bit, with this Poincaré notation, it makes it a little bit more elegant that I'm doing a quotient. And this one, it's just a bit more, it also, of course, has the quotient in it, the identifications, but just in a different way. Okay, and I think there, good? Good. I'm done for today.
Any questions?
Exactly, because right now, at this stage, you might have said, oh, so then these two things are the same.
How do you know?
You will have to wait until tomorrow, and tomorrow I will tell you why, even though I'm relating them by a diffeomorphism. So it's a question, exactly. Yeah, I raised that point. Like, why would I say that this is different, even though there's this diffeomorphism, and you might say, okay, maybe it's not defined everywhere, but it's still a diffeomorphism, right? So yeah, so how can we tell that these two are actually different configurations? And tomorrow I'll tell you why they are. No, oh, black holes? So it depends. It depends on what you. Tomorrow I'll write down more general metrics. So when we look at the perturbative part, we can. It also includes non-perturbative solutions, and so there's more general metrics that you can write down. But if you wanted something that is stationary, meaning that it has two killing vectors, dt and d phi, this is it, in the absence of matter. So if you want to have something that is not stationary, so it has less killing symmetries, then you can do more things. Or if you don't want it to have Lorentzian, perhaps, identification. So if you now have, if you say, oh, now in Euclidean signature, I have the torus, and then you can get excited, and you can do, for instance, what? Yes, exactly. And they will all solve the Einstein's equation. So you can have any higher genus topology that you want. The problem is that you're going to lose symmetry. So if you cut them to Lorentzian signature, they're not going to have like these two killing vectors, dt and d phi. But they're still solutions. And then also the Lorentzian continuations are tricky. So that's why you're also not going to have a global definition of time. But in Euclidean signature, basically, any Riemann surface you can that you want will basically be a solution. And this is also what causes a lot of headaches in AdS CFT, which I'm not going to tell you about, but it's one of the problems.
Can you also do any SHC transformation on these guys and get a solution?
And that we're going to use. That's a black hole fairy tale. So right now I just did one, right? So I did the S transform. We'll do the We'll do A, B, C, D with A times D minus BC equal to 1. Yes. Yes. That's called the SL2C family of black holes. But yeah.
All right, well, maybe I'll just remind you before we take our break that this week 4, like week 2, we have 4 lectures instead of 5, so there's going to be some empty slots. One of them is tomorrow morning at 9, so there's no lecture tomorrow at 9. We'll start at 10:45. We will have coffee before that. Speaking of coffee, we can break for that now. Let's thank Alejandra again.